Welcome! In this session, we'll tackle LeetCode problem number 685, Redundant Connection 2. This problem challenges us to identify and remove one edge from a directed graph to ensure it forms a valid tree. We'll explore the problem, break it down into manageable steps, and walk through the solution together. Let's get started. In this problem, we are working with a directed graph of n nodes, where each node is labeled from 1 to n. The graph has a specific structure. Every node can have at most one parent, except for one node that may have two parents. Your objective is to identify and remove exactly one edge in such a way that the graph becomes a valid rooted tree. Now, a rooted tree is defined as a directed graph where there is exactly one node, called the root, with no parent, and all other nodes in the graph must have exactly one parent. Additionally, every node in the graph must be reachable from the root. The input graph is provided as an array of edges, where each edge is represented as a pair, u, v. Here, u is the starting node, and v is the ending node of the directed edge. The task requires you to return the edge that can be removed to meet these conditions. If there are multiple valid edges, you should return the one that appears last in the input array. Let's look at an example. Consider the input edges equals 1, 2, 1, 3, 2, 3. Here, the graph has three directed edges, 1-2, 1-3, and 2-3. Notice that node 3 has two parents, node 1 and node 2, which violates the tree structure. To resolve this, we need to remove the edge 2, 3. By doing so, we get a valid rooted tree with the edges 1-2 and 1-3. In this new tree, node 1 is the root, as it has no parent, and all other nodes have exactly one parent. Furthermore, every node is reachable from the root. Hence, the output for this example is 2, 3. Now, let's examine another example with the input edges equals 1, 2, 2, 3, 3, 4, 4, 1, 1, 5. In this graph, there is a cycle involving the nodes 1, 2, 3, and 4. Specifically, the cycle is formed by the edges 1-2, 2-3, 3-4, and 4-1. To break this cycle and turn the graph into a rooted tree, we need to remove the edge 4, 1. Once this edge is removed, the graph becomes a valid rooted tree with the edges 1-2, 2-3, 3-4, and 1-5. Here, node 1 serves as the root, as it has no parent, and all other nodes have exactly one parent. The resulting tree satisfies all the conditions, so the output is 4, 1. There are some important constraints and edge cases to consider. First, the graph is guaranteed to have n edges, with n ranging from 2 to 10-4. Each edge is represented as a pair, u, v, where both u and v are integers between 1 and n. In terms of edge cases, if the graph has no cycle but contains a node with two parents, the edge creating the second parent must be removed. If the graph forms a cycle and all nodes already have one parent, the edge that closes the cycle should be removed. In scenarios where both conditions occur simultaneously, meaning there is a node with two parents and a cycle, we should prioritize breaking the second parent relationship first. This ensures that the resulting graph is always a valid rooted tree. To approach the problem of identifying and removing a single edge to turn a directed graph into a valid tree, we considered three primary scenarios. First, a node might have two parents, which violates the tree property that each node must have exactly one parent. Second, the graph might contain a cycle, which would also prevent it from being a valid tree. Lastly, it's possible for both issues to coexist: a node with two parents and a cycle in the graph. These scenarios guided us as we explored different strategies to solve the problem efficiently. One initial approach we considered was brute force. The idea here is straightforward. For each edge in the graph, we temporarily remove it and then check if the remaining graph forms a valid tree. A valid tree means no cycles and every node has exactly one parent. If removing an edge results in a valid tree, that edge is the redundant one. However, this approach has a significant drawback. Since we need to repeatedly perform cycle detection for each edge, the time complexity ends up being m*n, where m is the number of edges and n is the number of nodes. This makes it computationally expensive and impractical for the given constraints, where n can be as large as 10,000. Instead, we turn to an optimized union-find approach. Here, we make two key observations. If a node has two parents, one of the incoming edges must be removed. Additionally, we can use union find to detect cycles efficiently by determining if two nodes are already part of the same connected component. This strategy involves first identifying nodes with two parents and storing the conflicting edges. Then, we use union find to process all edges while skipping the first conflicting edge. If a cycle is detected, the second conflicting edge is redundant. Otherwise, the first edge is redundant. This approach has a linear time complexity of O(n), making it a much more efficient solution. The optimized union find approach was chosen due to its ability to handle all three cases, two parents, a cycle, or both, efficiently within the problem constraints. While depth-first search (DFS) is another viable option, it involves building the graph as an adjacency list and traversing it to detect cycles and validate tree properties. The process includes identifying nodes with multiple parents and removing the redundant edge. Although DFS has a similar time complexity of O(m + n), union find stands out as simpler to implement and debug for this specific problem. These factors made union find the preferred candidate over DFS. Ultimately, the optimized union find approach was selected for its balance of efficiency and simplicity. It handles all three scenarios, two parents, a cycle, or both, within linear time, ensuring it works seamlessly for the maximum constraints of the problem. Comparing union find with DFS, union find offers a more straightforward implementation and focuses specifically on connected components, making it easier to debug. When comparing union find with brute force, the advantages are even more pronounced, as brute force is computationally prohibitive for larger graphs. In summary, the union find approach is the most efficient and practical solution to this problem, achieving correctness without sacrificing performance or clarity. The objective of this problem is to identify and remove a single edge from a directed graph so that the graph becomes a valid tree. For a graph to qualify as a valid tree, it must meet three key criteria. It must be connected, meaning all nodes are reachable from each other, it must not contain any cycles, and each node can have at most one parent. To solve this problem, we need to handle three potential scenarios: a node with two parents, the presence of a cycle, or a combination of both issues. To begin, we parse the input edge list to construct the graph. As we do so, we track the parent of each node using a dictionary. If we encounter a node that gets assigned two parents, we note down the two conflicting edges for further processing. Next, we work to identify problematic edges by traversing the edge list. For each node, if it doesn't yet have a parent, we assign the current edge as its parent. If it already has a parent, we store both the current edge and the previous edge, as these are the conflicting edges. By the end of this step, we will have identified the two problematic edges or confirmed that the graph appears valid so far. After identifying these edges, we move on to detecting cycles using the union find data structure. This structure allows us to efficiently track the roots of nodes. For each edge, we attempt to unite the two nodes it connects. If the union operation fails, because the nodes already share the same root, a cycle has been identified, and we record the edge responsible for it. Finally, we resolve the issues based on the findings. If there are two parents but no cycle, we remove the second conflicting edge. If there's a cycle but no two-parent issue, we remove the edge causing the cycle, and if both issues exist, we remove the first of the two conflicting edges. Once the problematic edge has been resolved, we return it as the result. There are several key insights to keep in mind for this solution. First, union find is particularly well suited for cycle detection due to its efficiency. With optimizations like path compression and union by rank, its operations are nearly constant time. Second, when a node has two parents, addressing this conflict takes precedence, as it simplifies the problem and avoids unnecessary complications. Finally, the order of operations is critical. Resolving two-parent conflicts before checking for cycles ensures the algorithm produces correct results, since cycles can sometimes be a consequence of the two-parent issue. The data structures we rely on include union find for cycle detection, a parent dictionary for tracking node relationships, and an edge list for linear traversal. In terms of complexity, the time complexity is O(n), where n is the number of edges, as both union find and edge traversal are linear. Space complexity is also O(n), primarily for the parent and rank arrays used in union find. Let's consider an example to understand the algorithm in action. Suppose the input edges are 1, 2, 1, 3, 2, 3. First, we identify that node 3 has two parents, associated with edges 1, 3, and 2, 3. Next, we check for cycles using union find and detect a cycle involving edge 2, 3. To resolve the issue, we remove edge 2, 3, as it not only causes the two-parent conflict but also contributes to the cycle. The final output is 2, 3. This example highlights the importance of systematically identifying and resolving conflicts. It also underscores the need to handle edge cases, such as graphs with no conflicts, multiple overlapping cycles, or disconnected components. If the graph is already a valid tree, the algorithm should return an empty result. For multiple or overlapping cycles, the algorithm must ensure that the correct edge is removed to resolve all issues. Additionally, disconnected graphs are invalid and must be rejected, as connectivity is a fundamental requirement for tree structures. The implementation begins with the helper functions for union find. The find function uses path compression to locate the root of a node efficiently. The union function merges two nodes by comparing their ranks, ensuring the structure remains balanced for optimal performance. We then initialize a dictionary to track the parent of each node, as well as variables to store the two conflicting edges if a node has multiple parents. As we iterate through the input edges, we assign parents to nodes unless a node already has a parent, in which case we record the two conflicting edges. After this, we reinitialize the union find structure, setting up parent and rank dictionaries for all nodes. This prepares us to traverse the edge list again, this time focusing on detecting cycles and resolving conflicts. During the second traversal of the edge list, we skip the second conflicting edge temporarily to test if removing it resolves the issue. For other edges, we attempt to unite their nodes using the union function. If a union fails, it means we've encountered a cycle. At this point, if there's a recorded two-parent conflict, we return the first conflicting edge as the solution, since the second has already been skipped. Otherwise, we return the edge that caused the cycle. If no cycles are detected and only one of the conflicting edges was skipped, the second conflicting edge is returned as the solution. This logic ensures that the algorithm handles all scenarios correctly and efficiently. The final edge returned is the one whose removal resolves the graph's issues, making it a valid tree. Here, we start implementing the solution in Python. First, we define a class called solution with a method find redundant directed connection that takes a list of edges as input. Within this method, we define a helper function find which is used to locate the root of a node in the union find structure. This function follows the parent pointers recursively until it reaches the root node. Next, we define another helper function union, which merges two sets in the union find structure. The union function checks the roots of both nodes and attaches the smaller rank tree under the larger rank tree to keep the structure balanced. If the ranks are equal, we increment the rank of the new root. The main method then initializes variables, parent to track the parent pointers, rank to store the rank of each node, and candidate1 and candidate2 for storing potential edge removals later. We also declare an in-degree dictionary to keep track of nodes that may have multiple parents. Now, the first step is to identify if there is any node with two parents. We iterate over the edges and, for each edge, check if the destination node already exists in the in-degree dictionary. If it does, this means the node has two parents, so we store the conflicting edges in candidate1 and candidate2. Otherwise, we update the in-degree dictionary with the current edge. Next, we use the union find structure to detect cycles while iterating through the edges again. If the current edge is the same as candidate2, we skip it temporarily. For the other edges, if the union function returns false, it means we've found a cycle. In this case, if no node has two parents, we return the current edge as the redundant connection. Otherwise, we return candidate1 since removing it resolves both the cycle and the two-parent issue. If no cycle is found, we return candidate2, which fixes the two-parent problem. This completes the solution. Here, we start by importing the necessary Java utilities and defining our solution class. The main method, findRedundantDirectedConnection, takes a 2D array of edges as input. The goal is to return the edge that, if removed, would make the graph a valid tree. To begin, we initialize some helper arrays and variables. Parent and rank arrays are used for union find operations, while candidate1 and candidate2 will store potential edges to remove if we detect a node with two parents. We also create a hash map called inDegree to track the incoming edges for each node. The next step is to identify if there's a node with two parents. For each edge in the input, if the destination node already exists in the inDegree map, that means this node has two parents. In such cases, we store the conflicting edges in candidate 1 and candidate 2. Otherwise, we simply update the inDegree map with the current edge. After identifying nodes with two parents, we move to the second step, which is detecting cycles using the union find algorithm. For each edge in the input, we skip the candidate 2 edge if it exists, as it's a potential redundant edge. We then attempt to union the two nodes of the edge. If the union operation detects a cycle, meaning the two nodes are already connected, we return the edge causing the cycle if no double parent conflict exists. However, if a double parent scenario was identified earlier, we prioritize returning candidate 1, the earlier edge. This ensures we handle both cases of graph invalidity, cycles and nodes with two parents. If there's no cycle and no other conflicts, we proceed to return candidate 2, since it's the edge we skipped earlier. The union find helper methods, find and union, are critical for detecting cycles and maintaining the graph structure. The find method uses path compression to optimize the lookup of a node's root parent, ensuring efficient queries. The union method merges two sets based on their rank, which represents the height of the tree rooted at each node. If the roots of the two nodes are the same, it means adding this edge would create a cycle, so we return false. Otherwise, we merge the smaller tree into the larger one to maintain balanced structures, updating the ranks accordingly. If the ranks are equal, we increment the rank of the new root. Once the union is complete, we return true to indicate that the edge was successfully added without forming a cycle. To solve this problem, we start by analyzing the given input, which is a set of edges 1, 2, 1, 3, 2, 3. The first step is to identify if any node has two parents. We process each edge one by one. When we process edge 1, 2, node 2 gets its parent as 1, so we update the inDegree to 2, 1. Next, for edge 1, 3, node 3 gets its parent as 1, so now the inDegree becomes 2, 1, 3, 1. Finally, when we process edge 2, 3, we see that node 3 already has a parent, which is 1. This means node 3 now has two parents. We record the two conflicting edges. Candidate 1 is 1, 3, which was the first edge assigning parent 1 to node 3, and candidate 2 is 2, 3, the current edge attempting to assign parent 2 to node 3. With these candidates identified, we move on to checking for cycles using the union find data structure. We initialize the parent array as 0, 1, 2, 3, where each node is its own parent initially, and the rank array as 0, 0, 0, 0. Processing the first edge, 1, 2, we perform a union of nodes 1 and 2, so the parent becomes 0, 1, 1, 3, and rank updates to 0, 1, 0, 0. For the next edge, 1, 3, we union nodes 1 and 3, updating the parent to 0, 1, 1, 1, and keeping the rank as 0, 1, 0, 0. Finally, we skip candidate 2, which is edge 2, 3, to check if this resolves the issue. After skipping this edge, the tree remains valid, so we conclude that candidate 2, the edge 2, 3, is the redundant connection and return it as the result. In this example, we analyze a case where the graph contains a cycle, but no node has two parents. The input edges are 1, 2, 2, 3, 3, 1. First, we check if any node has two parents by processing the edges. As we iterate, we observe that no node has more than one parent, so the inDegree values are 2, 1, 3, 1, 1, 1. With no node having two parents, we move on to detecting cycles using the union find method. We initialize the parent array as 0, 1, 2, 3, and the rank array as 0, 0, 0, 0. For the first edge, 1, 2, we union nodes 1 and 2, updating the parent to 0, 1, 1, 3, and rank to 0, 1, 0, 0. Then, processing edge 2, 3, we union nodes 2 and 3, resulting in the parent array 0, 1, 1, 1, and rank remaining 0, 1, 0, 0. Finally, we process edge 3, 1. At this point, we detect a cycle because both nodes 3 and 1 share the same root. Since there are no candidates recorded in this case, we directly return the last edge that caused the cycle, which is 3, 1. This example involves both a node with two parents and a cycle. The input edges are 1, 2, 2, 3, 3, 4, 4, 2, 1, 5. To begin, we determine whether any node has two parents. As we process the edges, we see that no node is assigned two parents, so the in-degree values remain consistent for each edge processed. Specifically, node 2 has in-degree 1, node 3 has in-degree 1, node 4 has in-degree 1, and node 5 has in-degree 1. Since no node has two parents, we now shift our focus to detecting cycles using the union find algorithm. To analyze the time complexity of our solution, we consider the main steps of the algorithm. First, we identify nodes with two parents by iterating over all the edges. This requires just one pass through the input, where each edge is checked once, resulting in O(n) time complexity. Next, we perform union find operations for the edges, excluding the second candidate edge if it exists. Each union operation involves two find operations, which use path compression to make them nearly constant time, O(1) in practice. Since there are n edges, the total time for all union find operations is O(n). Finally, returning the result is a simple constant time operation, O(1). These components together form the basis of the algorithm's time complexity. Combining these steps, the overall time complexity of the algorithm is O(n). The dominant factors contributing to this are the single traversal of edges and the union find operations, both of which scale linearly with the number of edges. Now, looking at space complexity, the parent and rank arrays are central to the union find structure. These arrays store information for all nodes, requiring O(n+1) space to accommodate nodes from 1 to n. Additionally, the in-degree dictionary is used to map nodes to their parents for detecting nodes with two parents. In the worst case, this dictionary contains an entry for each node, contributing O(n) space. Lastly, a few additional variables like candidate 1 and candidate 2 require only constant space, O(1). Therefore, the total space complexity is dominated by the parent, rank, and in-degree structures, giving us O(n). When comparing approaches, a naive solution would involve explicitly constructing the graph and repeatedly traversing nodes and edges to check for cycles or nodes with multiple parents. This method could require O(n)² time in the worst case because each edge insertion might trigger a full traversal of the graph. In contrast, the optimized approach we've described leverages union find with path compression and rank optimization to reduce the time complexity to O(n). This improvement is significant, as the union find structure efficiently handles connectivity checks and cycle detection. Additionally, the space complexity of O(n) is much more scalable than the potential overhead of constructing an adjacency list or matrix, which could require more memory depending on the graph representation. Analyzing the algorithm further, the best-case scenario occurs when the graph has no nodes with two parents and no cycles. In this case, the algorithm simply processes each edge once and performs union find operations, resulting in O(n) time. For the average case, the time complexity remains O(n), as the algorithm's performance is determined by the structure of the graph rather than specific edge or node values. Even in the worst-case scenario, such as a fully connected graph with both a cycle and a node with two parents, the algorithm's efficiency holds. The edge traversal and union find operations still require O(n) time, and the space usage remains bounded at O(n), making the solution robust and consistent across all cases. To understand the efficiency of the union find structure, we consider the mathematical reasoning behind its time complexity. The find operation benefits from path compression, which ensures that its amortized complexity is O(alpha(n), where alpha(n) is the inverse Ackermann function. This function grows extremely slowly, making it effectively constant for all practical inputs. Consequently, n union find operations collectively take O(n) time. Additionally, since each edge is processed only once during the graph traversal, this step contributes O(n) time as well. Combining these factors, the overall time complexity of the algorithm is O(n). The space complexity also remains linear at O(n), making the solution both time and space efficient for handling graphs of this nature. When tackling this problem, there are several common mistakes to watch out for. First, it's essential to account for the two-parent scenario. A node with two incoming edges is a key indicator that you need to address before detecting cycles. Ignoring this step can lead to misidentifying the redundant edge. Next, be cautious about how you modify the graph during testing. Some approaches destructively remove edges, which can make debugging harder or lead to incorrect results. Instead, simulate edge removals temporarily without permanently altering the graph structure. It's also important to remember that this is a directed graph problem. Treating the input as undirected can result in improper cycle detection or edge removal. Another pitfall is failing to respect the problem's requirement to remove the last redundant edge. Removing edges in the wrong order can invalidate your solution or produce an incorrect tree. Lastly, avoid the temptation to overcomplicate the solution. While advanced algorithms like Tarjan's SCC might seem appealing, this problem can be effectively solved with simpler approaches like union find combined with basic graph traversal techniques. Now, let's consider some valuable insights for interviews. First, always focus on edge cases. Interviewers often test how your solution handles scenarios like nodes with two parents, self-loops, or graphs that are already valid trees. This is a great opportunity to demonstrate your ability to think critically. Mastery of the union find algorithm is another key area to highlight. Be ready to explain concepts like path compression and union by rank, as they are central to solving this problem efficiently. Additionally, interviewers appreciate when candidates discuss trade-offs between approaches. For instance, while union find is highly efficient for this problem, methods like DFS or BFS might be more intuitive, even if less optimal. Lastly, clarity is paramount. Walk through your solution step by step, especially how you identify and remove the problematic edges. This will help the interviewer understand your thought process and ensure no crucial details are overlooked. Related problems like redundant connection, graph valid tree, and course schedule are also worth studying, as they share similar concepts and techniques. There are also alternative approaches to solving this problem, each with its own strengths and weaknesses. The union find approach is highly efficient, with a time complexity of O(n) when using path compression. However, it can be slightly tricky to adapt union find for handling the two-parent scenario, so careful implementation is required. Another option is using DFS or BFS for cycle detection. These methods are often easier to understand and implement, but they tend to be less efficient, with a worst-case time complexity of O(n squared). For those looking to strike a balance, a hybrid approach can be effective. By combining union find with a separate check for nodes with two parents, you can achieve both clarity and efficiency. However, this approach requires special attention to avoid redundant checks and ensure all edge cases are handled properly. Each of these methods has its place, so choose the one that aligns best with your strengths and the problem's constraints. Great work! We've successfully solved LeetCode problem number 685, Redundant Connection 2. We covered graph traversal techniques, cycle detection, and edge removal strategies. Remember to apply these concepts to similar problems. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more problem walkthroughs. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!